Okay, for those of you who missed class because of testing, we did a little review on arithmetic sequences. And if you recall, if I have a sequence such as the one showing here, 20, 24, 28, 32, 36, etc., I know this is an arithmetic sequence because to go from one term to the next, I'm going up by 4 each time. And we call that a common difference, and we designate a common difference with the letter D. The recursive formula for a common difference is a to the n equals a to the n minus 1 plus d, where n is greater than 2. So let's talk about what that means. Okay, if I'm looking for any number, I have to take that number and subtract 1 from it and add the common difference to it. So a1 is 20. a2 then is going to be 20 plus my common difference, in this case 4. So a2 is going to be 4. Okay, now I can kick into my recursive formula where a3 is a3 minus 1 plus 4. 3 minus 1 is 2, so I know that 2 is 24. My second position is 24, so 24 plus 4 equals 28. Go down for a4. A to the 4 minus 1, which is the same as a3, is going to be 28 plus 4, which is 32, etc. As you can see, it's like going up a ladder. You have to be on the rung before you to get to the next one. So to overcome the cumbersome of it's difficult. If I'm looking for, say, the 50th term, to use this formula, I would have to get all the way up to the 49th term to be able to use it. So instead of that, we go to what's called the explicit formula. And the explicit formula says if I'm looking for a to the n, I take my first term, add n minus 1 times my common difference to it. So if I'm looking for my 50th term, n becomes 50. My first term is 20. Plus 50 minus 1, which is 49, times my common difference of 4. So my 50th term will become 20 plus 196, which is 216. I could also turn this into a generic formula by saying I'm just looking for a to the n. Well, a to the n equals a1 plus n minus 1, comma d. Okay, so a to the n is still going to be my first term of 20 plus n minus 1 times 4 now. I'm going to distribute the 4, so a to the n equals 20 plus 4n minus 4. Now I'm going to simplify, and I'm going to rewrite it with my variable term in the first position, so that's going to be 4n plus 16. Okay, and this, I can take any value for n, substitute it in here. So here, if I wanted to know the 50th term, I would say 4 times 50 plus 16, which would give me the same thing as that I got up here, would be 216. Either way is acceptable. But what I'd like for you to notice is to go back to this step here. And what does that look like to you? Hopefully you see that it looks a lot like y equals mx plus b, where and this acts the same way as x and y do in that equation. So what this boils down to really is that this does form a algebraic function. And if you were to graph, going back to up here, okay, if this was my output, my input would be the order that they're in. This would be 1, 2, 3, 4, and 5. Okay, these would be my x terms, this would be my y terms, and in fact I could graph it and I would get a straight line. So it is a linear function. Okay, this was in chapter 3. If you want to go back and practice doing some problems, that's where you'll find it. Okay, what we're doing now is we're moving on to what's called a geometric sequence. And you'll notice here that I do have a sequence, 2, 6, 8, 54, 162, etc. There is a pattern here, but I'm not adding or subtracting a common difference. Instead, I have what's called a common ratio. And I get that by taking a term, and this time the second term, divide it by 2, and I get 3. Okay, I need to check all of my terms, so I would do 18 divided by the term in front of it and get 3. Same thing with 54, divided by 18 and get 3, and 162 divided by 54 would also give me 3. So notice that these are fractions and fractions are ratios. So instead of having a common difference, I would have a common ratio. And we just refer to that as R, and in this case my common ratio is 3. Okay, the recursive formula for a geometric sequence is written in the form a to the n equals a to the n minus 1 times my common ratio So once you know the common ratio in a geometric sequence, you can write the recursive form for that sequence. Okay, and it would just be the same as that I have A1 would equal 2, and then A2 would equal 2 times 3, which is 6, and then A3 is going to have to equal A3 minus 1 times the ratio of 3, which is going to be 6 times 3, which is 18. A4 then is going to be A4 minus 1 times 3, which is 18 times 3, which is 54, etc. Just like we did in the arithmetic sequence. There's no difference. We have to know the term before in order to build onto our sequence. Okay, and just like in the arithmetic sequence, we can go to a explicit formula. But before we go there, I want you to think about what's going on up here. Is that from here to here, I am multiplying times 3. From here to here, I am multiplying times 3. From here to here, I am multiplying times 3. And from here to here, it's times 3. Okay, so I really have 3 times 3 times 3 times 3. And what does that look like? Well, I think if I had it times x times x times x times x, you would very readily go to, well, that's x to the 4th. And it's the same thing here. This would become 3 to the power of 4. Okay, and that is the difference between an arithmetic sequence and a geometric sequence. In the geometric sequence, in my explicit formula, and let me write it here, a to the n equals a1 times r, but now I take into account for this n minus 1 becomes an exponent. Okay. Alright, so a to the n equals my first term times my common ratio to the power of whatever term I'm looking for minus 1. So let's go back to our sequence and say that I wanted to find the 10th term. Okay, Well, it would be A10 equals A1. In this case, A1 was 2, times my common ratio of 3, and to the 10 minus 1. So A10 would be 2 times 3 to the 9th power. So A10 would become 2 times 19683, which would be 39,366. So my 10th term then is 39,366. Okay. Notice how much quicker my sequence grew. Okay, to go to 10, I went to 39,000. Where in my arithmetic sequence I would have only been going up by 3 or 4 each time, and it would have taken me a long time to get to there. Okay. Okay, suppose we're asked to find the explicit formula. For a sequence where R equals 2 and A12 equals 14,336. Okay, we actually have all the information that we need to know to be able to do that, because we know the explicit formula is a to the n equals the first term times the common difference, the common ratio, times n minus 1. All we have to do is go and substitute in what we know. Well, we know this is the 12th term, so a to the 12th would be 14,336 equals, we don't know a1, so we would leave that a1. Okay, but we know that our ratio is 2, and we know that our term is 12, and it would be minus 1. So 14,336 equals first term times 2 to the 11th power. And 2 to the 11th power then is going to be 2,048. Now all I have to do is solve for, let me move this up. Now all I have to do is solve for A, divide both sides by 2,048, and my first term is 7. I can now write my recursive formula, because I know that a to the n is going to equal my first term, which is 7, times 2 to the n minus 1. Okay? And that would be the formula that I could use to find any term in this sequence that has a common ratio of 2 and a first term of 7. Okay, that's pretty much it. There was homework assigned only for the geometric sequence. You want to go ahead and take a look at that and make sure you don't have any questions on it. See you in class.